Adaptability in the face of dynamic and unknown environments is a vital feature of any systems that we design to interact with our human world. To date, this remains a major hurdle in the development of robotic systems, with many robotic systems failing when brought out of the lab into a new environment. On the other hand, a wide range of animals can perform these tasks, locomoting in unknown and ever-changing environments and manipulating objects for the sake of hunting or survival, from a very young age. Part of the difficulty in these tasks arises from the mismatch between the range of frequencies used for movement and the range of frequencies experienced during perturbations. In the case of impulsive collisions like catching a ball, these systems can experience force frequencies up to 1,000s of Hz, while the majority of human and large animal actions range from 0 to the tens of Hz. What the human hand has that makes reacting to these frequencies possible, and that robotic systems often neglect, is viscoelasticity. In the case of the human hand, this passive damping occurs in the joint capsules between different segments of the fingers, and the active damping occurs in both the intrinsic and extrinsic muscles that articulate the fingers. We wanted to know how vital these elements were to getting a robotic to successfully perform grasping tasks without the use of a high-frequency controller. Specifically, we considered two research questions. 1. Does adaptive damping, stiffness in joints and actuators allow for selective filtering of perturbation frequencies? 2. Does there exist an optimal range of viscoelastic properties that simultaneously achieve high-frequency damping and controller phase shift compensation? This led us to our hypothesis. Relative to purely elastic joints, introducing viscous joint damping into a human hand-inspired grasper will decrease the time to stable catch. B. The level of joint damping that maximally decreases the time to stable catch will be within the range of observed human values. To explore the effect of this damping and stiffness, we built a human hand-inspired 5-fingered grasping robot with added damping and stiffness. The 3D printed robotic hand was designed to mimic the structure of the human finger, with concentric snap-fit features that allow digits to be assembled to form a hollow rotary knuckle into which viscous damping joints can be inserted. Stiffness is applied to the system using dragon skin 30 stretched across the exterior length of each finger. Articulation is tendon-driven using Kevlar cables and a motor. The system is set up to track a falling ball with a laser proximity sensor, and incrementally close the fingers in time to catch it. The addition of a passive elastic element to the fingers turned out to be vital to achieving concurrent flexion and therefore successful completion of grasping tasks. Initially, we observed the behavior of the tendon-driven fingers during contraction without the presence of series elastic elements. When actuated, the finger articulates beginning from the distal joints first and only demonstrates articulation in the more proximal joints once the former has maximized its rotation. With this type of motion, the robot cannot catch anything. However, when the elastic element is introduced to the back of the fingers, all 3 joints now rotate simultaneously. This translates to concurrent flexion of the entire finger and results in more organic movement that enables the fingers to grasp around an object. Our robot can now articulate its fingers concurrently and reach for objects. This organic, almost human motion allows the robot to catch a small test ball with ease. In order to introduce viscous joint damping into the finger joints of the robotic hand, we designed and fabricated damper inserts which slide into the finger joints. Parametric sweeps of the free geometric parameters were performed to determine the level of damping that could be achieved. These parametric sweeps allowed us to determine the viscosity required to achieve near human levels of joint damping. Due to the very small geometry of the dampers, the required viscosity of the working fluid was very high. To achieve this high viscosity, Jif peanut butter was chosen as the working fluid and used for all of the fabricated dampers. Now, with our 3-fin concentric dampers filled with peanut butter, we could analyze the effect of viscous damping on the system. First, we performed pendulum tests with modified finger joints to characterize the frictional and damping properties of the system. Without a damper, the system is significantly underdamped and oscillates repeatedly. However, with our peanut butter damper, the system becomes nearly critically damped. When we compare these cases, we see that we have nearly achieved the behavior of viscous damping in an actual human finger. When we performed catch tests with the actual robot, we expected to see that the undamped case fails to secure a falling ball, while the damped case securely arrests the motion of the ball. However, we were not able to observe an increase in catching performance in the experimental trials, though there are a number of mitigating factors that may have impacted these results, including sensitivity of the hand to the tension in the tendons, further controller tuning, and increasing the ball mass to increase the energy entering the system. Overall, our hand was just too awesome. Next steps for our team will include continued modeling and simulation efforts to gain more insight into the frequency behavior of the system during dynamic tasks, and improving mechanical robustness of the hand. Thank you to Vicky Webster Wood and the rest of the 24,775 teaching team for their help on this project. One small step for bio-inspired robots, one giant catch for robotic hands everywhere.